Okay, so here we are to finish up the notes for continuity, and we're starting with, well, continuous functions, this definition in your notes. So first of all, continuous functions can be defined two different ways. Way number one is on what's called a closed interval. So if it's on a closed interval, that means it's on an interval from some value A to some value B. Okay? Now, if it's on a closed interval and you're using brackets, so these brackets, okay, that represents that you include the endpoints. So we talked about earlier, if the endpoints are inclusive, basically, then it is continuous at that point. So then if it's brackets, your graph is going to look like that. So then that means that it's continuous at its endpoints. So remember, brackets are continuous. Closed interval from A to B, they use parentheses, then that means you have a graph that looks like this. They're open. So then it's discontinuous at its endpoints. Okay, so there's a difference. And then you can have any combination, like continuous at A but not B, whatever. Okay, continuous function, then closed interval could also be an open interval. Let's do this in a different color. Open interval. So then you only have one option, and that goes from negative infinity to infinity. And so if it's an open interval, they're not going to give you the whole negative infinity to an infinity part, or they may just give you this, and you have to assume that it's an open interval. Okay. So continuous functions are on some interval. They have to be on an interval. Okay. And then also continuous functions are continuous at every single point in its domain. And all of these, whether it's closed or open, are all of the possible x values. That's your domain. Here are some properties of continuous functions. If you know the functions f and g are continuous, then any of these following combinations have to be continuous. So if you take function f and function g and add them, they have to be continuous. So x squared is continuous. And x squared plus 4 is continuous. So if you take x squared plus 4, you have a continuous function. So let's say f is x squared. X to the third is continuous as well. So let's say g is x to the third. These are both continuous. We know they are. And so if you add them, subtract them, multiply them, or multiply them by any constant, or divide them, given that g of z does not equal 0, then you are going to have continuous functions. Okay, these rules are pretty important. Give you a lot of shortcuts in the future that if you remember those rules. All right, so let's take a look at, first of all, composite functions. Remember, composite function is if you plug a function inside of another. So basically what this states is that if you know, for example, g of x here, if you know g of x is continuous and you know f of x is continuous, you can put g inside f or f inside g or whatever, you know then you have a continuous function. Very similar to the last set of rules, whereas if you add, subtract, multiply, divide them, this is the same thing. Okay, and I have a little example here for you. You can look at that on your own. And then lastly, before we do some examples here, pretty important theorem here, simple to understand. Let's say you have a function that goes from A to B. Okay, so then that means that it starts at a y value of f of A and ends at a y value f of B. And between A and B, it can look like anything as long as it's a function, vertical line test, passes that. So let's say it just looks like this then. That's our function. Okay? Doesn't matter what it looks like. Anyway, what this says is you have a function that's drawn here. It's continuous on a closed interval. So you notice I was able to draw that without picking up my pencil at any single point. And it takes on every value between f of a and f of b. So you know every single y value, okay, here is accounted for on this graph. Some of them more than once, and that's fine. That's not a problem. Some of them more than once. Okay, and that's all the intermediate value theorem for continuous functions represents. So if you know that it's continuous, then it has to take on every single y value. And I could have easily drawn a straight line from a to b as well. Okay, but it has to take on every single y value. All right. So try to think, before we move on, try to think of some times when this theorem would not be true. And the only time this would not be true is if the function is not continuous. And that's a simple answer there. Okay, that's the only time this would not be true, is if the function was not continuous. Go ahead and try this example then. What I want you to do is look at the function. You have a piecewise function. Find each point of discontinuity if they exist. You don't know if they do or not. And then B, which of them are removable, not removable, if you were able to find any. So go ahead and try this on your own and then come back here and see how you did. So on A, find each point of discontinuity. So this is a piecewise. So there are different parts. There's actually 3 parts to this graph. So let's look at each part. So you're going to look at 3 minus x, and in order, okay, to see if they're discontinuous, there we go, you want to check to see if the y values of these functions are equal. Check to see if the y values, for example, the 3 minus x, looking at this value of 2. When I plug 2 in there, it's 3 minus 2, and that's 1. This one obviously is 2, but then what about the x over 2? When I plug 2 in there, it's equal to 1. So these y values are the same. So what that means is the graph does something like this. There's a hole there, but at 2, you notice, at 2, because with your 3 minus x, this function, this is not equal to 2, so it's an open circle. And then also with this function, it's just greater than, it's not equal to, so it's open. But it's the f of x, the actual value of the function of 2 at y x equals 2 is y equals 2. And so it's up here 1. Okay, so the graph is going to look, I know this isn't like these two, but anyway, it's going to look something like this. Okay, where these are going to connect. However, okay, there's a hole between them because neither of them are equal to the value of 2 at that point. So they jump up. Okay, so in this case, you would check all of your possible connection points for your Frankenstein or your piecewise function. And now, looking at your graph, you can tell that at 2, it's removable. Because if you look back in your notes, that's what a removable discontinuity looks like. Okay, and so these are one-sided limits. Okay, if it's removable, that means that you have the same y value when x is equal to 2, except for this. But these two values have the same y value, so your one-sided limits are the same. So the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right. These are what we call one-sided limits. Wait for the computer to catch up. All right, and these are popular questions on the AP exam as well. One-sided limits determine if they're the same or not. Okay, so it's not continuous at 2. It's removable because the one-sided limits are the same. So give yourself a minute. Pause the video, write all that down in your own words. If you have trouble with that, ask me in class tomorrow or next time I see you. One more example. And again, try this one on your own, but first of all, let me just explain what an extended function is. An extended function is basically a simplified or factored. I'll just say factored. And in this case, the continuity or the discontinuity is removed. So that's what an extended function is when the discontinuity is removed. All right, so go ahead and try to figure that one out. And if you need a hint, go ahead and hang on a little bit. But try to figure it out on your own first, and then come back and see how you did. If you need a hint, factor. Factor the top, factor the bottom. Okay, that's the end of your hint. And here's the answer. The top factors into x squared plus x plus 1 times x minus 1. And you can graph it to see where your zeros are, whatever you want to do. But then the bottom factors into x minus 1 times x plus 1, like that. So you notice the x minus 1's cancel, and you're left with just the x squared plus x plus 1 all over x plus 1. So this right here that we have now, that is your extended function, because it's the exact same function. And I want you to try this. Try it. Graph x to the third minus 1 over x squared minus 1, and graph x squared plus x plus 1 all over x plus 1, and tell me that they're not the exact same function. The only difference is that at x equals 1, so at this point, this function has a hole. The original one has a hole, but this new function, you remove the hole. Okay, which doesn't make any sense since a hole is empty space. Anyway, but you removed it. You removed that empty space by filling it in somehow. Okay? Anyway, so they are the exact same thing, but this one highlighted in pink is what we call the extended function. Okay, so in these notes we did extended functions, more on one-sided limits, which are really important, and most important is the intermediate value theorem for continuous functions. All right, good luck, and let me know if you have any questions in class.